important problem related to flows is the min-cut problem. You may be familiar with the max flow min-cut theorem. We're not going to prove that theorem here. Instead, we're just going to introduce the idea of cuts and show that this min-cut problem is actually the dual of the max flow problem. In the cut problem, we're given the same information as in a max flow problem. We're given a directed graph, G equal to VA, and we're given capacities on each one of the arcs, UA. We're also given a start node S and a termination node T. Our objective now is to, instead of finding a flow along the arcs from S to T, to find a cut between S and T. A cut is a subset of vertices, and the idea is that S is on one side of our cut, T is on the other side of the cut, and the arcs that go between nodes in C to nodes out of C are the cut arcs. The value of a cut is the value of the sum of the capacities along the arcs that are cut. That is, for every arc such that one node is in C and the other node is outside of C, we include that arc inside of our cut. So here we have our input example. We have our directed graph, and we have the capacities on each one of these arcs. You'll note that this is the same example that we used in the max flow problem. That's because the input to the max flow and min cut problem is exactly the same. In this case, the cut that's going to be minimal is the one that's going to include just S. This is our cut C, and it's equal to the node S. To compute the value of this, we look at all the arcs that are cut. In this case, all the arcs emanating out of S are the ones that we're going to sum up when evaluating the value of our cut. In this case, the value of our min cut is equal to 4. We can also see that there's more than one min cut here. If, for example, we were to take the node S and include one additional vertex, let's call this additional vertex A, the value of this is still equal to 4. The idea here is now that the arcs coming out of this new cut, this pink cut, is the arc coming out of S, but also the arcs coming out of A. So we have to sum up the quantities along all of these arcs. An important piece of notation we can use to sort of clarify things is the idea of a cut arc. We're going to denote the set of cut arcs as delta C. That is, delta C are all the arcs that are emanating out of the set C. These are the arcs that we're going to sum up when we sum up the value of a cut. To be formal, this is the set of all arcs so that I is in C and J is not in C. That is, this is an arc that goes from inside of C to outside of C. Not surprisingly, we can model the minimum cut problem as an integer program. This integer program is going to have two types of variables. There'll be a yi variable for every node, and there'll be an xij variable for every arc. The idea is that yi is equal to 1 whenever I is in our cut C. Note that if there was a variable for s, ys, that ys would automatically be 1 because s is always in C. The variable xij is going to indicate whenever the arc ij is a cut arc. That is, when I is in C and j is not in C, xij should be equal to 1. We can now go through the integer program. The objective function of our integer program is straightforward. We'd like to minimize, among all the cut arcs, the total capacity across the cut arcs. So we'd like to minimize xij, uij. The first constraint is going to be indicative of all the constraints that we write. That is, if we have some node j, there's two possibilities. Either yj is equal to 1, in which case j is on the same side of the cut as s, or the arc from s to j is equal to 1. That is, the cut C that we're going to create cuts this arc. For example, when we look at our graph, a particular point that exhibits this behavior is j, let's say. And j, in this case, is on the same side of the cut as s, and so the arc sj is not cut. On the other hand, if we were to look at, say, node I, then we have that I is on the opposite side of the cut, so yj is equal to 0. And so the arc from S to I has to be equal to 1. That's what this constraint is encapsulating. The second constraint is in a similar spirit. Again, if the node j is on the same side of the cut as t, then the arc jt isn't cut. Otherwise, the node j, if it's on the same side of the cut as s and the opposite side is t, then we have to increase the value of that xjt variable to 1 because the arc jt is cut. Finally, the third constraint says the same thing about two arbitrary nodes. In this case, we can exhibit this point in our graph. Suppose we have additionally the point k. If we consider this constraint for jk, it says that either both nodes j and I have to be on the same side of the cut, or the variable xij has to be a cut arc. To see this, in this particular example, yj would be equal to 1, yk would be equal to 0, so the sum yj plus yk is equal to 1, and so xij has to be set equal to 1 in order to satisfy this constraint. Finally, all the y's and x's have to be on our lattice of 0 and 1. This integer program formulates the maximum cut problem. The final thing we'd like to show is that the max flow problem and the min cut problem form a dual pair. In this case, we're just going to look at the linear programs. So now we have the linear programming relaxation of the min cut problem written over here. If we looked at our max flow linear program and we took the dual in the mechanical way, we would end up with the minimum cut problem. So if we look at the linear programming relaxations of both of these problems, we have that the optimal solution of our flow is equal to the optimal solution of our cut. Of course, this is in the linear programming world. If we look in the integer programming world, as long as we have integer solutions, that is, when we have uij all integers, we know that our max flow problem has integer values. And since our flows have integer values and our cut value is equal to our flow problem, we're going to have that our cut has an integer value. This implies that z of c is equal to an integer value. So although these form a dual pair in the linear programming world, because of this property, that integer solutions, or rather integer data implies integer solutions in the flow problem, we get that these actually form a dual pair in the integer programming world also, provided that the data is all integers. In the next lecture, we're going to see a very powerful theorem that's going to prove, in a more general setting, that these problems actually form a dual pair in the